Welcome to Physics Lab number 2, Investigating Resistive Forces by Ethan Tremmel and John Robertson.
The main problem we are investigating in this experiment is that metal ball bearings appear to reach different terminal velocities, if at all, when falling through different fluids of different viscosities. Our goal was to use Tracker to analyze videos of metal ball bearings falling through different viscosity fluids to find their terminal or max velocity. We hypothesized that the velocity of the falling ball would be inversely proportional to the viscosity of the fluid, and our results supported our hypothesis, showing that there was an inverse relationship between viscosity and velocity of the ball.
Viscous force is the force that slows the object's acceleration in the fluid. It becomes constant after the object reaches terminal velocity, which applies Newton's second law, which force of viscosity equals force of gravity. So we asked what determines this terminal velocity, and our initial investigations resulted in viscosity having a relationship.
To be more specific about viscosity, viscosity is the flow or the internal flow of each liquid. Different fluids will have different viscosities, so we're examining do different viscosities create different terminal velocities, and what is the relationship between these two variables.
So our system schema for this experiment includes the metal ball bearing, the fluid, and the ground. The metal ball bearing has a contact force with the fluid, which is our viscous force, and the metal ball bearing also has a gravitational force with the ground. The fluid also has a gravitational force with the ground, but in this experiment we won't measure that.
The force diagrams represent the ball at or not at terminal velocity. When the ball is at terminal velocity, it represents Newton's second law that the viscous force is equal and opposite to the gravitational force, meaning that there is no acceleration and a constant velocity. When the ball is not at terminal velocity, the force of gravity is greater, indicating that there is an acceleration in the negative direction with gravity.
Our models also included the energy pie charts in the experiment. So initially the ball is still stuck to the magnet, so it has some internal energy and some gravitational energy. When it starts to fall, its gravitational energy decreases and its kinetic energy increases, and it keeps increasing when it falls down. However, when terminal velocity is reached, the kinetic energy stops increasing and the internal energy increases while the gravitational decreases. But if it isn't reached, kinetic energy will keep increasing.
For our experimental design, the trials had consistent metal ball bearings, volume of graduated cylinders, magnets, and heights, and tracker that was used to find the velocity. Now the differences came in the fluid that the ball was dropped through. Our procedure for our experiment was to fill the graduated cylinder with 40 milliliters of fluid, use the magnet on the outside to hold the ball in position, record the video, drop the ball, import the video to Tracker to find the velocity, and repeat for every fluid.
The implications of our experimental design were that we were targeting the terminal velocity when looking at our models. So when it reaches constant velocity, our Fnet is equal to 0 and our kinetic energy is constant. Our anticipated limitations were that the graduated cylinder wasn't high enough, so that way we wouldn't reach terminal velocity in each fluid.
Here is the table of compiled terminal velocity and viscosity data for each fluid.
So this is our graph of the data. It shows an inversely proportional trend line to the data. This means that two variables always multiply to a constant. Unfortunately, Google Sheets and Excel couldn't create an inversely proportional trend line. However, we estimated this line to be negative 0.43925 divided by mu, which equals the terminal velocity, using our mass, radius, and our force equation.
When conducting our experiment, we ran into our anticipated error of the height not being tall enough to reach terminal velocity in each fluid. An additional error that we ran into was the limitation of the camera of being able to see slow or very quickly moving balls traveling through the fluid.
So our physics connection is that different viscosities do create different terminal speeds according to our data. Using our general trend line, we can see it's an inversely proportional relationship, which means the variables must multiply to a constant. This constant has to relate to the viscous force and the radius of the ball, since both of those are constant and make the units of viscosity times terminal speed constant. This force is related to our force equation of viscous force, and that supports our hypothesis.